Today's topic is acid-base chemistry, and in particular, I want to talk about how organic acid-base chemistry fundamentally is different than the way we think about general chemistry, acid-base type reactions. And what I'm thinking about here is more the way we describe how the reaction happens. The reactions themselves are, of course, the same, but one major difference between organic chemistry and general chemistry is in general chemistry, we're largely focused on reasonably strong acids and reasonably strong bases, whereas in organic chemistry, what we have is incredibly weak acids,
which means incredibly strong bases.
Another major difference is that organic acid and base doesn't happen in water, which changes things, whereas in general chemistry, what we're largely focused on is in water solution. So those are going to be a couple of differences. So in particular, you see W, what I mean is weak, S, what I mean is strong. So here I'm saying strong acid versus strong base. And so what I've illustrated so far on the board is the reaction of a classic strong acid, one of the six strongest acids, HCl, with a strong base, NaOH. And of course, from general chemistry, you should remember that react a strong acid with a strong base, and what you'll make is water and a salt. And in organic chemistry, I'm much more interested in describing how this reaction takes place than anything else, whereas in general chemistry, we were more focused on doing math with it and calculating pH and stuff like that. But if I'm going to be doing a mechanistic understanding of this acid-base reaction, then what I really need to do is to figure out where all the electrons are and then draw out the actual mechanism for the reaction. And so you'll note that I have drawn HCl as having a bond there, and that is a good general rule. If you are going to use a hydrogen in a reaction, or if it's going to participate in a reaction, then you need to draw out what it is bound to make the arrow pushing easier. But the other thing that's really helpful to do, and this is generally true when you're doing mechanisms, is to draw in where all the lone pairs are. And so you should recognize that this chlorine has 3 lone pairs on it, and this oxygen has 3 lone pairs on it. So that's one way of starting to figure out what the mechanism is going to be. The other thing I want to point out is that very frequently, if you see sodium in a reaction mechanism in organic chemistry, you should think of that as being sodium plus. And so rather than thinking of the sodium and the oxygen as having an actual covalent bond, you're better off thinking of this as sodium plus that happens to be right next to hydroxide minus. In other words, don't think of sodium hydroxide as a single unit, think of it as 2 separate entities that are going to be associated near each other in space because they have opposite charges and therefore are attracted to each other. Alright, so mechanistically, if you're going to describe how this happens, what you do is you say, well, this oxygen is going to be the source of electrons that's going to end up attacking this hydrogen. And the reason why that's happening is because this hydrogen, as drawn, has a reasonably large delta plus on it right now. It is got a substantial amount of partial positive, and that's because this chlorine has a substantial amount of delta minus. So you draw that arrow going into the hydrogen, but as you draw that, what you're going to need is to break the bond, because the hydrogen can only tolerate having one bond at a time. So if you're creating a bond, what you are doing is breaking the bond. And you should be thinking about the orbitals involved here. What's actually doing the attack is a sp3 orbital on this oxygen, and this is the highest occupied molecular orbital on the oxygen. And so this oxygen is serving as a nucleophile, as a source of electrons. And that source of electrons is then going to attack the electrophile in the system. And in particular, what's being attacked in this system is the HCl sigma star anti-bonding orbital. And the reason why this bond ends up breaking is because you're attacking the anti-bonding orbital for the HCl bond. So as you fill the anti-bonding orbital with these electrons, that will cause the HCl bond to break. In other words, you are attacking the lowest unoccupied molecular orbital, which in this case is the sigma star. And this is a good general description of the mechanism of an acid-base reaction in organic chemistry. You're almost always going to be taking a lone pair, and a lone pair is going to be the highest occupied molecular orbital for whatever structure you're dealing with. It's a non-bonding orbital, so it's relatively high energy. So that's going to be doing the attacking. And in general, you're going to be plucking off a proton. And the reason why you're able to do that is because this has got to be a relatively acidic proton, which means it's got to have a substantial amount of delta plus already. And therefore, you're going to attack that H whatever sigma star, fill that LUMO, and cause the bond to break. And so all of that is what's happening. You can see that the oxygen is combining with that hydrogen to make water. And you can see that the Cl minus is just plain left over. And the way you should think of the sodium chloride over here, again, is not as though they are bound, but simply that they are associated with each other reasonably closely in space, mostly because their charges are attracted to each other. So what's going on there is not an actual bond, just they are floating near each other. Okay, now imagine that I ask you to predict the products between this weak acid acid and this strong base. And once again, if you were thinking about this in general chemistry terms, you'd be interested in the equilibrium constant for this reaction, except that in general chemistry terms, we would again describe this as being a reaction that goes fully to the right. This will just fully react, and that's because you have a strong base and a relatively weak acid. So we just simply assume it goes to completion, and then we figure out what the pH will be after the fact. But once again, in organic chemistry, I'm not interested in the math so much. What I'm interested in, does this reaction go, and how far does it go, and what is the mechanism by which it goes? And so it won't surprise you at all to see that all of this data remains the same. The nucleophile, the place where the arrow starts, is going to be an oxygen sp3 orbital, which is the highest occupied molecular orbital. Again, the lone pair is going to be the nucleophile, and once again, since the nucleophile is the same in both cases, I can draw the same exact arrow. Now, of course, there's going to be some differences over here. This is still going to be the electrophile, and in particular, in this case, it's going to be the HO sigma star that's actually the electrophile. So it's the HO sigma star that is the LUMO, and that's why it's the one that gets attacked. But since you're filling the sigma star, what you're doing again is breaking the OH bond. Those electrons have to go somewhere. They end up going to become a lone pair on the oxygen, and that's the mechanism for this reaction. This then generates acetate ion, and of course, though I'm not going to draw the resonance form, as soon as you see a circumstance with double bonds and extra lone pairs, you should immediately think to yourself, yeah, resonance is possible, and spread that around. And meanwhile, what's left over here is going to be water, and then an unreacted sodium ion. And that sodium ion is not actually going to make a bond to the acetate, but is going to be associated to it, and they will be reasonably close to each other in space. All right, I'm not quite ready to put us into a fully organic context yet, but now we're getting closer to an organic context where you have the acetic acid reacting with, say, water itself. And again, the reason why this isn't purely organic is because we usually don't have water in organic reactions, but we are now in the realm of weak acid reacting with weak base, which is much more similar to organic context. So let's now focus in on this reaction wherein acetic acid is reacting with water. And in a general chemistry context, you would be interested now in the Ka, the acid dissociation constant for this reaction. And in fact, this is an acid dissociation sort of reaction where you take an acid and you react it with water in order to see what it makes and to see how far this reaction goes. And so the Ka for reactions of many weak acids with water is listed in tables, and so you can look it up and find that Ka is 1.8 times 10 to the minus fifth. And so the question is, how far does this reaction go? And the answer, since this is a very small number, is it doesn't. This reaction is not a particularly good equilibrium reaction. In fact, equilibrium lies almost entirely to the left. There are way more reactants than there are products. What are the products? Well, in a general chemistry context, you would just simply say, well, I'm going to have acetate ion, and I'm going to have H3O plus, and you know that because that's what the definition of an acid dissociation sort of reaction is. So the kind of reaction that gives a Ka is simply the formation of H3O plus and the counter ion of the weak acid. So you would describe this as being Ha, and you would describe this as being its conjugate base, A minus. And we always in Gen Chem will call it Ha and A minus, or alternatively you might call it B for base and HB plus. The same idea. But anyhow, acid, conjugate base, base, conjugate acid. Again, for the purposes of organic chemistry, what I'm interested in is the actual mechanism of this reaction, and so I draw out the lone pairs involved. And once I've drawn the lone pairs, I would then say, well, the oxygen sp3 orbital is still going to be the highest occupied molecular orbital of the nucleophile, and the water is going to be the nucleophile. Just keep in mind, it's a much weaker nucleophile than the O- was. This has a desperate need to make a bond to make its minus charge go away. This doesn't particularly want to react because it'll end up making a plus. But you still have excess electron density on that oxygen. That's still in an sp3 orbital, and that's still the highest occupied molecular orbital for the molecule. And of course, all the analysis that I did down below still applies. I'm going to be attacking the OH sigma star, which is the lowest unoccupied molecular orbital. So as I'm making a bond to this H, what I'm doing is filling that OH sigma star, which causes the sigma bond that is there already to break, and the electrons, which were between the hydrogen and the oxygen, now become an oxygen lone pair. pair. And so in the end, I have 3 lone pairs on this oxygen, which is why it's a minus, and in the end, I have a new hydrogen on this water, which only has 1 lone pair now, and that's why it is plus. And again, in organic chemistry, I'm mostly interested in mechanism, and in general chemistry, I'm mostly interested in math. However, we're going to be dealing with such tiny numbers in organic chemistry that actually it's not useful to think in terms of KAs, because these are all going to be extremely small numbers. So instead, we simply think in terms of pKa, and as you'll recall from general chemistry, I hope, p is the function negative log of something. So if I have a pKa, what I have is the negative log of the Ka. So I'm taking the negative log of the Ka, and the pKa for acetic acid HA expression is 4.76, which I will remember simply as 5. The pKa for a generic carboxylic acid in the land of organic chemistry is 5. But again, the whole point of all this so far is organic chemists are mostly interested in the mechanism, and then to a lesser extent whether this reaction goes or doesn't go. And we're not interested in the math per se, but in what the math tells us about whether this reaction goes to the right or not. And a pKa of 5 at this point really tells us this reaction does not go. It ends up pretty far to the left, which is what the Ka, being a very small number, 10 to the minus 5th, is telling us. This reaction does not go, not to any appreciable extent. Although I should qualify that. If we're dealing with 10 to the 23rd molecules, because we have about a mole of stuff in solution, then with 10 to the 23rd molecules, even a very small Ka like this suggests that we have at least a substantial number of molecules in this state, even though the vast bulk of them are in this state. Almost all of them are over here, but we still have a decent number of this. So 10 to the minus 5th does say most molecules are like that, but also means we have a fair number of these just because we have 10 to the 23rd molecules, or maybe 10 to the 21st if we're working on millimole scale rather than mole scale. We have huge numbers of molecules, which means that this reaction can in fact take place to some small extent, just not very far. And now we're finally arriving at a purely organic reaction, in this case reacting acetic acid with ammonia, and this is still kind of an inorganic reaction, but at least what makes it organic is that you can run this in the absence of any water. So what happens if you just simply mix these two together? And again, from an organic perspective, what we're interested in is mechanistically, how does this behave? And the only thing that changes now, of course, is that the HOMO is going to be a nitrogen sp3, but this is still nitrogen serving as the nucleophile. And so the nitrogen serves as a nucleophile, and it's creating a bond to, once again, the sigma star orbital of the OH bond, which of course means that that bond is going to break. And as that bond breaks, what it does is become a lone pair on the oxygen. And so we end up generating, of course, exactly the same thing as above, with 3 lone pairs on this oxygen and a minus charge on the oxygen. And meanwhile, the other thing that you generate is now an ammonium. This nitrogen picks up a 4th hydrogen atom, and now that it has 4 hydrogen atoms bound to it, it will become positively charged, and we just simply call that ammonium. All right, so if you have ammonia reacting with acetic acid, in principle, mechanistically, what you generate is acetate and ammonium. And so now the real question is, does this reaction go? Where does equilibrium for this reaction lie? Is this something that proceeds mostly to products, or is this something that stays more on the reactant side? When you mix these two together, does the reaction happen or not? So again, what we're interested in from an organic perspective is mechanistically what's happening, and also which direction does this lie? And you can calculate that, which is going to be the subject of another video. But the real question when you're doing those calculations isn't the number itself. It is instead, does this reaction happen? Because if the reaction happens, then that has implications for how this goes on to react and do other things. And if it doesn't, then you know maybe this reaction doesn't happen. So that's why we care about acid and bases in organic, is what reactions will take place down the line from them. And so the question that we're really interested in, can you deprotonate this with this base or not? Or if you mix these two together, which way will it end up? What is K equilibrium for this process? That's what we're interested in.